It began with music and champagne. A summer evening in Kansas City, 1981. The Hyatt Regency Hotel's atrium shimmered like a cathedral made of glass and steel, except above the crowd, hidden inside the ceiling, a single washer was carrying twice the weight it was designed for. The lobby stretched 117 feet high, taller than a 10-story building. Marble floors reflected thousands of lights. Glass elevators rose like transparent towers along the walls. 2 suspended walkways crossed the space, bridges hanging in midair connecting the hotel tower to the function rooms on the opposite side. Every Friday evening, the Hyatt hosted tea dances, big band music, swing dancers, couples in their 50s and 60s who remembered when this music was new. On July 17, 1981, somewhere between 1,600 and 2,000 people filled the lobby. The band played on a mezzanine platform. Dancers swirled on the marble below. Meanwhile, guests lined the railings of the suspended walkways, the second-floor span and the fourth-floor span, looking down at the celebration like spectators in a floating theatre. The fourth-floor walkway held approximately 40 people. The second-floor walkway, directly below it, held about 20 more. These weren't small structures. Each walkway stretched 120 feet long and 8 feet wide. Massive concrete decks wrapped in steel, suspended by hanger rods that disappeared into the ceiling above. To the guests standing on them, the walkways felt solid, permanent, safe. Except they weren't. At 7:05 p.m., the band was playing Satin Doll, a Duke Ellington standard that had been making people dance since 1953. Some guests on the walkways were bouncing slightly to the rhythm. Others stood still, drinks in hand, watching the crowd below. Wayne Lishka and his wife stood on the second-floor walkway. They felt a vibration. Something didn't feel right. They stepped off, walked toward the solid ground of the mezzanine. 30 seconds later, the walkways fell. The sound wasn't an explosion. Witnesses described it as a series of sharp cracks, like gunshots echoing through the atrium, followed by a rushing noise of falling steel and concrete. Then silence. The music stopped. The glass elevators stopped. For 3 seconds, 64 tons of suspended walkway structure crashed through the lobby, the fourth-floor span slamming into the second-floor span, both collapsing together onto the marble floor below. 114 people died. 216 were injured. But the story of how those walkways fell, and why, didn't begin that Friday evening. It began 2 years earlier, in an engineering office, with a single line on a drawing that no one properly checked. This is the story of how precision engineering failed, how modern architecture betrayed the people it was supposed to protect, and how one unchecked revision, a change so small it seemed insignificant, buried 114 lives under steel and concrete. The truth, investigators would discover, was hidden in the mathematics of load transfer, a problem so simple that engineering students could calculate it, except no one did. The Hyatt Regency was supposed to be Kansas City's crown jewel. The project was launched by Crown Center Redevelopment Corporation, a massive urban renewal effort funded by Hallmark cards to revitalize downtown Kansas City. The hotel cost $150 million to build, 40 stories tall, 750 rooms. It opened in July 1980 exactly 1 year before the collapse. The architectural firm was PBDML, Patty, Berkebiel, Nelson, DeStefano, Maklowitz, and Lewis. A Kansas City-based practice known for modern, dramatic designs. The structural engineering was handled by GCE International, specifically the firm of Jack D. Gillum and Associates. Gillum was a licensed professional engineer in Missouri with decades of experience. The project engineer assigned to the Hyatt was Daniel M. Duncan, also a licensed PE. The design concept was ambitious. The atrium, that soaring 117-foot vertical space, would be the heart of the hotel. Glass elevators would carry guests up through the open air, and crossing the atrium at the 2nd and 4th floors would be suspended walkways, allowing guests to move between the hotel tower and the meeting spaces without descending to the lobby. These walkways weren't decorative. They were functional circulation routes. They had to carry people, furniture, equipment. The building code required them to support at least 100 pounds per square foot, a standard load for public assembly spaces. The original design, created in 1978, was straightforward. Each walkway would be suspended by 6 pairs of steel hanger rods, essentially long threaded bolts anchored into the roof structure. The critical detail was this: a single continuous rod would pass through both walkways. Here's how it worked. The rod would be anchored to the ceiling beams. It would pass through the 4th floor walkway structure, through the box beam that formed the walkway's edge, with a washer and nut holding the 4th floor walkway in place. Then the same rod would continue downward, passing through the 2nd floor walkway with another washer and nut holding that walkway. At the bottom, a final nut would secure the entire assembly. In this configuration, each connection point carried only the weight of one walkway. The upper connection, at the 4th floor, held only the 4th floor walkway. The lower connection held only the 2nd floor walkway. The load was distributed. The engineering calculations showed this design was safe, with appropriate safety factors, with room for error. Except that's not what got built. In the summer of 1979, the steel fabrication drawings, called shop drawings, were being prepared by Havens Steel Company, the contractor responsible for manufacturing and installing the walkway structure. Shop drawings are detailed construction documents that show exactly how components will be fabricated and assembled. They're based on the engineer's design drawings, but they include the fabricator's specific methods and dimensions. Someone at Havens Steel looked at the original design and saw a problem. Threading a single continuous rod through both walkways, a rod that might be 60 or 65 feet long, would be difficult. The rod would have to be inserted from below, threaded through the lower walkway, then through the upper walkway, then connected to the ceiling. It was awkward, time-consuming. So Havens proposed a change. Instead of one long rod, they would use 2 shorter rods. The upper rod would run from the ceiling to the 4th floor walkway. The lower rod would run from the 4th floor walkway down to the 2nd floor walkway. The 2 rods would be connected at the 4th floor level. This seemed simpler, cleaner. Each rod could be installed independently. Except it changed everything. In the revised configuration, the upper connection, at the 4th floor, now had to carry both walkways. The lower rod was hanging from the upper nut, which meant the upper nut was supporting not just the fourth-floor walkway, but also the second-floor walkway hanging below it. The load had doubled. The shop drawings showing this revision were sent to GCE International for review. This is standard procedure. Engineers review shop drawings to ensure they match the design intent. On the Haven steel shop drawings, project engineer Daniel M. Duncan made his mark, initialing the drawings, indicating review and approval. But no calculations were performed, no load analysis, no comparison of the original single-rod system versus the revised two-rod system. Duncan later testified that he did not recognize the significance of the change. He saw 2 rods instead of 1 rod, but he didn't calculate what that meant for the connection. Jack Gillam, the principal engineer, later stated he never saw the revised hanger rod detail. The firm's internal procedures apparently didn't require him to review every shop drawing. Duncan, as project engineer, had the authority to approve them. So the change went through, 2 rods instead of 1. Construction proceeded through 1979 and 1980. The walkways were assembled on the ground, then lifted into position. The hanger rods were installed. The connections, the washers and nuts bearing against the box beams, were tightened. Inspections were performed. The walkways passed. On paper, everything looked fine. The hotel opened in July 1980. For 13 months, guests walked across those suspended walkways. Thousands of people. Tea dances every Friday. Conferences, weddings, meetings. Meanwhile, at the fourth-floor connection points, the nuts were holding 61,000 pounds. They were designed to hold 31,000. No one knew. July 17, 1981 was a typical summer Friday in Kansas City. Hot, humid, the kind of evening where air conditioning felt like a gift. The Hyatt Regency's lobby was the coolest place downtown. That soaring atrium with its climate control and marble floors. The tea dance started around 6 p.m. The band, a local big band group, set up on the mezzanine and began playing swing standards. Glenn Miller, Benny Goodman, Duke Ellington, music that had been making people dance since the 1940s. By 7 p.m., the lobby was packed. Estimates vary. Some witnesses said 1,600 people. Others said closer to 2,000. Dancers filled the floor. Others watched from the mezzanine levels. Many stood on the suspended walkways, leaning against the railings, looking down at the scene below. The walkways were popular viewing platforms. You could see the entire lobby from up there. Watch the dancers spin, see the glass elevators rise. It felt special. Except the walkways were bouncing, not violently, just a slight vibration when people moved. Some guests noticed it. Most didn't think anything of it. These were suspended structures. Of course they'd have some flex. That's normal, right? At approximately 7:05 p.m., the band was playing Satin Doll. Wayne Lischka and his wife were standing on the second-floor walkway. Lischka later told investigators they felt the structure moving more than usual. Not swaying, something else. A vibration that didn't feel right. His wife said she wanted to leave. They walked off the walkway onto the solid mezzanine floor. Less than a minute later, The fourth-floor walkway failed. The failure initiated at one of the hanger rod connections on the fourth-floor walkway. The nut, bearing against a washer, which was bearing against the box beam, pulled through, punching shear failure, investigators would later call it. The washer, instead of distributing the load across the box beam's top surface, punched through the steel like a fist through paper. Once one connection failed, the load shifted to the remaining connections. They were already overstressed. They failed in rapid sequence. Within seconds, all 6 connection points on the fourth-floor walkway gave way. The fourth-floor walkway dropped. It fell approximately 20 feet, the distance between the fourth floor and the second floor, and slammed into the second-floor walkway below. The impact was catastrophic. The second-floor walkway's connections, designed to hold only the second-floor structure, couldn't withstand the sudden dynamic load of a 25-ton walkway crashing down from above. Both walkways fell together. The fourth-floor structure and the second-floor structure, now a combined mass of 64 tons of steel and concrete, crashed onto the lobby floor. People on the walkways had no warning, no time to react. One moment they were watching dancers, the next moment they were falling. People on the lobby floor below had no chance. The walkways fell onto the densest part of the crowd, the area directly beneath where people had been gathered, watching the band. The total time from first failure to final impact, approximately 3 seconds. Survivors describe a sound like thunderclaps, sharp cracks as the connections failed, then a rushing, roaring noise as steel and concrete fell through the air, then impact, a massive crash that shook the entire building. Then silence. The band stopped playing. The music cut off mid-note. For several seconds, no one moved. People couldn't process what had just happened. The walkways had been there, solid, permanent, and now they were gone. In their place was a mountain of twisted steel, shattered concrete, and bodies. Then the screaming started. The Kansas City Fire Department received the first emergency call at 7:06 p.m. Structural collapse at the Hyatt Regency. Multiple casualties. The first units arrived within minutes. Firefighters entered the lobby and stopped. The scene was unlike anything they'd trained for. The atrium, which had been a pristine showpiece of modern architecture, now looked like a war zone. The 2 walkways had pancaked onto the lobby floor, creating a debris field of bent steel beams, crushed concrete, shattered glass, and blood. The immediate problem: no one knew if more of the building would collapse. The remaining walkways, there was a third-floor walkway that hadn't fallen. Were they stable? Were the ceiling anchors secure? Could rescuers safely enter the debris field? Fire Chief Richard Sheets made the decision to begin rescue operations immediately, despite the risk. People were trapped in the wreckage, screaming for help, alive. Firefighters crawled into the twisted steel with cutting torches, hydraulic spreaders, and bare hands. The debris was unstable. Steel beams shifted as rescuers moved. Concrete slabs tilted. Meanwhile, survivors trapped beneath called out, guiding rescuers to their locations. One firefighter later described cutting through a steel beam and hearing a voice say, "Thank you," from beneath it. Then silence. The person had died while the rescuer worked. The rescue operation continued through the night. Portable lights were brought in, turning the atrium into a harsh, shadow-filled workspace. Cranes were positioned outside the building, ready to lift large sections of debris once rescue workers cleared victims. Medical teams set up triage stations in the hotel's meeting rooms. Ambulances formed a line outside. The last living survivor was pulled from the wreckage at approximately 2:30 a.m. on July 18th, more than 7 hours after the collapse. By dawn, the recovery operation shifted from rescue to body retrieval. 114 people were dead. The bodies were taken to a temporary morgue. Identification would take days. Many victims had been crushed so severely that visual identification was impossible. 216 people were injured. Burns from the band's stage lights, which had fallen with the walkways, crush injuries, broken bones, lacerations. Many survivors were trapped for hours beneath steel beams, suffering pressure injuries that would lead to amputations. The scene at local hospitals was chaotic. Every emergency room in Kansas City was overwhelmed. Blood banks put out urgent calls for donations. The lines stretched around blocks. By midnight on July 17th, blood supplies were overflowing. Kansas City residents had donated more than could be used. Meanwhile, at the Hyatt, investigators from multiple agencies had already begun arriving. The Kansas City Building Department, the Missouri Division of Fire Safety, the National Bureau of Standards, the Occupational Safety and Health Administration. Everyone wanted to know what happened. And more importantly, whose fault was it? The National Bureau of Standards, now called the National Institute of Standards and Technology, led the technical investigation. Dr. Edward O. Frang, chief of the Structures Division, headed the team. They arrived in Kansas City within days of the collapse. The first question was obvious. Did the walkways fall because of poor materials, bad steel, defective concrete? Investigators collected samples from the wreckage. Steel specimens were sent to laboratories for tensile testing. Concrete cores were analyzed. Welds were examined under microscopes. The results came back negative. The materials were fine. The steel met specifications. The concrete was properly mixed. This wasn't a materials failure. The second question, was it a construction defect? Were the walkways built incorrectly? Investigators examined the failed connections. The hanger rods were in place. The nuts were properly sized. The washers were there. Everything had been assembled according to the shop drawings. The construction workers had done their job. Which led to the third question. Were the shop drawings wrong? This is where the investigation focused. Investigators obtained the original design drawings from GCE International. They obtained the shop drawings from Havens Steel. They laid them side by side and compared. The difference was immediately obvious. Original design, single continuous rod through both walkways. Each connection carries the load of one walkway only. Shop drawing revision, 2 separate rods. Upper connection carries the load of both walkways. Dr. Frang's team performed the load calculations. The 4th floor walkway weighed approximately 24 tons. The 2nd floor walkway weighed approximately 19 tons. Together, 43 tons, roughly 86,000 pounds, distributed across 6 hanger rod connection points. Each connection carried approximately 14,300 pounds from the walkway's dead load alone. But that's not all. Building codes require considering live load, the weight of people and furniture. For public assembly spaces, the code required £100 per square foot. The fourth floor walkway was 120 feet long and 8 feet wide, 960 square feet. At £100 per square foot, that's £96,000 of live load. Add the dead load. Each connection at the fourth floor had to support approximately £30,000 under full code load. The actual capacity of the connection, as built, approximately £18,900. The connection was loaded to 60% of its ultimate capacity during normal use. No safety factor, no margin for error. Add people bouncing to music, creating dynamic loads. And the connection was at failure. In the original single-rod design, each connection only carried one walkway's load. The capacity was adequate. The design worked. But in the revised two-rod design, the upper connection carried double the load, and no one had calculated what that meant. The National Bureau of Standards report, published in 1982, was unambiguous. The walkway collapse was caused by a connection failure at the fourth floor walkway hanger rod supports. The failure was the result of a design change that was not accompanied by appropriate structural analysis. In simpler terms, someone changed the design without doing the math. The report identified secondary issues. The welds connecting the box beam to the walkway structure were undersized. They didn't meet the original design specifications. This made the connection weaker than it should have been. But, even with perfect welds, the connection couldn't have carried the revised load. The welds didn't cause the collapse. The doubled load did. The investigation's conclusion was brutal. The walkways, as built, were not capable of supporting the minimum loads required by building codes. They were unsafe from the day they were installed. For 13 months, thousands of people had walked across those walkways, never knowing they were standing on overstressed steel connections that could fail at any moment. The question of legal responsibility was more complicated than the technical failure. In November 1984, the Missouri Board for Architects, Professional Engineers, and Land Surveyors held hearings to determine whether Jack D. Gillum and Daniel M. Duncan had violated professional standards. The hearing transcripts reveal the defense arguments. Duncan testified that he reviewed the shop drawings but did not recognize that the change from a single rod to 2 rods created a load path change. He saw it as a fabrication detail, a matter of how Haven's steel would assemble the components, not a structural modification. He admitted he did not perform calculations on the revised detail. Gillum testified that he never saw the revised hanger rod detail on the shop drawings. The firm's procedures delegated shop drawing review to project engineers. Duncan had the authority to approve shop drawings without Gillum's direct oversight. Gillum maintained that the responsibility for the design error rested with Duncan, who approved the change, and with Haven Steel, who proposed it. Haven Steel's position was straightforward. They fabricated and installed the walkways exactly as shown on the engineer-approved shop drawings. They didn't make unauthorized changes. They followed the approved design. In February 1986, the Missouri Board issued its ruling. Both Jack D. Gillum and Daniel M. Duncan were found to have engaged in gross negligence, misconduct, and unprofessional conduct in the practice of engineering. Their professional engineering licenses were revoked. The revocations were later modified. Both engineers had their licenses reinstated with probation and conditions. Duncan's license was reinstated in 1989. Gillam's was reinstated in 1991. Both were required to complete ethics courses and operate under supervision. GCE International, the engineering firm, did not survive. The firm dissolved in the aftermath of the collapse. Meanwhile, the civil lawsuits proceeded. More than 200 plaintiffs sued Crown Center Redevelopment Corporation, the hotel owner, PBNDML, the architectural firm, GCE International, Haven Steel, and various other contractors and consultants. The legal process took years. In the end, settlements totaled approximately $140 million. The hotel's insurance covered most of the payouts. Crown Center Redevelopment absorbed significant losses. The architectural firm survived, but was permanently scarred by association with the disaster. Criminal charges were considered, but never filed. Prosecutors determined that while the engineering failures were egregious, they didn't rise to the level of criminal negligence. The engineers had made mistakes, catastrophic mistakes. But there was no evidence of intentional misconduct or willful disregard for safety. The legal outcome was unsatisfying for many survivors. No one went to jail. The engineers eventually got their licenses back. The companies paid money and moved on. But the engineering profession was transformed. Within months of the collapse, engineering schools across the United States added the Hyatt Regency case to their curricula. It became required study in structural engineering courses, professional ethics classes, and engineering management programs. The American Society of Civil Engineers conducted its own analysis and published case studies. Engineering licensing boards revised their standards for professional responsibility. Shop drawing review procedures were formalized across the industry. The critical change was this: engineers could no longer treat shop drawings as simple fabrication details. Any change from the original design, even changes proposed by fabricators, required explicit structural review and calculation. The phrase "reviewed for general conformance only" was no longer acceptable on shop drawing stamps. Engineers had to specify exactly what they reviewed and what they didn't. Peer review requirements were strengthened. For major projects, particularly those involving innovative structural systems, independent engineers were required to review designs. The single engineer approval model that allowed Duncan to approve the shop drawings without oversight became professionally unacceptable. Professional liability insurance requirements increased. Engineering firms were required to carry higher coverage limits and demonstrate quality control procedures. Insurance companies began auditing firms' shop drawing review processes. The Hyatt Regency collapse entered the profession's collective memory as the defining example of what happens when checks fail, when assumptions go unchallenged, when small changes aren't properly analyzed. At universities, professors use the case to teach a simple lesson. Every line on a drawing represents a load path. Every load path must be calculated. Every calculation must be checked. The walkway collapse became shorthand for professional responsibility. "Don't let this be another Hyatt" became a warning in engineering offices. The hotel itself struggled to recover. Immediately after the collapse, the Hyatt Regency closed. The lobby was a crime scene, a disaster zone. For weeks, investigators worked through the wreckage. Structural engineers assessed the remaining building. The question everyone asked: was the rest of the hotel safe? The investigation found that the collapse was limited to the walkways. The hotel's primary structure, the tower, the floors, the exterior walls, was sound. but the atrium would require complete reconstruction. By August 1981, the hotel began limited reopening. Guest rooms in the tower were accessible. Meeting spaces were functional. But the lobby remained closed, blocked off behind temporary walls. The decision about the atrium was difficult. Should the suspended walkways be rebuilt? Crown Center Redevelopment decided no. The suspended walkways would not be replaced. Instead, the atrium would remain open, a vertical space without the crossings. Guests would use elevators and stairs to move between tower and meeting spaces, but they would not walk across suspended bridges. Temporary support columns were installed to shore up the remaining third-floor walkway, which hadn't fallen. It remained in place, but was no longer accessible to the public. The Hyatt Regency fully reopened in late 1981, approximately 5 months after the collapse. The atrium was redesigned with plants, fountains, and seating areas on the ground level. The space that had once held 2,000 dancing guests was quieter now, more subdued. For survivors and victims' families, the hotel's continued operation was painful. Some couldn't understand how the building could remain open. Others appreciated that the hotel provided jobs and economic activity for Kansas City. The hotel operated for 40 years after the collapse. It changed names, from Hyatt Regency to Sheraton. Ownership changed, management changed, but the building remained. In 2021, the hotel closed for extensive renovations. The Sheraton brand invested millions in updates. The hotel reopened in 2023. Now called the Sheraton Kansas City Hotel at Crown Center. The atrium still stands. The vertical space is still there. But the suspended walkways are not. Every July 17th, survivors and victims' families gather at a memorial outside the hotel. The Skywalk Memorial Foundation organizes the remembrance services. Names are read. Flowers are placed. Silence is observed at 7:05 p.m., the moment of collapse. The memorial itself is simple. A stone marker lists the 114 names. The inscription reads, "In memory of those who lost their lives in the Hyatt Regency Skywalk's collapse, July 17th, 1981. For survivors, the trauma never fully healed. Many developed post-traumatic stress disorder. Loud noises triggered panic. Enclosed spaces became unbearable. Some survivors couldn't enter hotels for decades. First responders suffered too. Firefighters who worked the rescue operation, pulling bodies from wreckage, hearing voices go silent, carried those memories for life. Several developed PTSD. Some left the fire service. Kansas City's fire department eventually established peer support programs for traumatic incidents, directly influenced by the Hyatt experience. Attorney Robert Gordon, who represented many of the victims' families in civil litigation, later reflected on the case. He noted that the monetary settlements, while substantial, couldn't restore what was lost. Parents who lost children. Children who lost parents. Spouses who lost partners. The money provided financial security, but it couldn't provide healing. Some survivors became advocates. They testified before legislative committees on building safety. They spoke to engineering students. They shared their stories to ensure the lessons of July 17th, 1981 would not be forgotten. One survivor, Lee Payton, who had been on the second-floor walkway and was trapped in the wreckage for hours, later said, I want engineers to know that their calculations aren't abstract. They're not just numbers. They're lives. Every time an engineer signs a drawing, they're signing for the safety of real people. My children, my wife, me. The Hyatt Regency walkway collapse remains one of the deadliest structural failures in United States history. Only the collapse of the I-35 bridge in Minneapolis in 2007, which killed 13 people, comes close in recent memory. But the Hyatt was different. It wasn't a bridge failure. It wasn't weather-related. It was a building, a modern, recently constructed hotel that failed during normal use. The technical failure was simple. A load path change doubled the stress on a connection. The connection couldn't handle the load. It failed. But the systemic failure was complex. It involved assumptions about professional responsibility, gaps in communication between designers and fabricators, inadequate review procedures, time pressure during construction, cost considerations, and ultimately, a signature on a shop drawing without the calculations to back it up. Daniel M. Duncan's testimony haunts the engineering profession. I did not recognize the significance of the change. That phrase, did not recognize, became the profession's nightmare, because it meant that experience, credentials, and good intentions weren't enough. Engineers had to actively check, calculate, verify. The assumption that a fabricator's proposed change was benign, that 2 rods instead of 1 was just a construction detail, proved fatal. In engineering schools, professors emphasize this point. Never assume. Always calculate. If you don't have time to check, don't approve. If you don't understand the change, don't sign. The Hyatt Regency case is taught alongside other engineering disasters. The Tacoma Narrows Bridge, the Quebec Bridge, the Hartford Civic Center roof collapse. But Hyatt holds a special place because the failure was so preventable. No new physics, no unprecedented loading, no extreme weather. Just a load path change that a sophomore engineering student could have flagged, if anyone had bothered to check. The American Society of Civil Engineers estimates that approximately 50,000 structural engineering students have studied the Hyatt Regency case since 1981. Textbooks include detailed analyses. Case study competitions use it as a scenario. Ethics courses require written reflections on professional responsibility. At the University of Kansas, less than an hour from Kansas City, civil engineering students visit the Hyatt Memorial as part of their curriculum. They stand at the site, read the names, calculate the loads, understand what went wrong. Professor John Smith, who teaches structural engineering at Kansas State University, tells his students, "The Hyatt Regency walkways didn't fail because the engineers were incompetent. They failed because competent engineers made assumptions. They trusted. They didn't check. And 114 people died. Your job is to never let that happen again." The case also influenced building codes. The International Building Code, which most U.S. jurisdictions have adopted, includes specific provisions for suspended structures. Connection design requirements were strengthened. Load factors were increased. Inspection requirements for structural steel connections were formalized. Professional engineering licensing exams now include questions on shop drawing review responsibilities. Engineers taking the PE exam must demonstrate understanding of when changes require reanalysis. The National Council of Examiners for Engineering and Surveying added ethics scenarios based on the Hyatt case. The impact extended beyond engineering. Architecture programs teach the case as an example of coordination between design disciplines. Construction management courses use it to emphasize the importance of understanding design intent. Project management programs examine it as a case of communication failure. The lesson transcends the technical details. It's about responsibility, about checking your assumptions, about recognizing that a signature on a document means accountability. In 2019, the American Society of Civil Engineers published a retrospective on the Hyatt Regency collapse. The article, written by engineers who had studied the case for decades, included an interview with one of the original investigators. He said, "We see structural failures periodically. Bridges collapse. Buildings suffer damage in earthquakes, but those are usually load conditions that exceed design parameters. The Hyatt was different. The walkways failed under loads they should have been designed to carry. They failed during normal use. That's the nightmare scenario for any engineer." The retrospective noted that in the 40 years since the collapse, structural engineering practice had fundamentally changed. Quality assurance programs were standard. Peer review was common. Software verification was required. The profession had learned. But the article warned against complacency. New materials, new construction methods, new technologies. Each generation of engineers faces new challenges. The lessons of the Hyatt Regency: check your work, question your assumptions, calculate everything, remain relevant. At the National Institute of Standards and Technology, in a secure archive, the original investigation files are preserved. Photographs of the wreckage, lab reports on the failed connections, calculations showing the load path analysis, testimony transcripts, the complete record of what happened and why. These files are available to researchers, engineers, and students. NIST maintains them as a public service, because the best way to prevent future failures is to understand past ones. The Hyatt Regency case file is one of the most frequently requested records in NIST's archives. On July the 17th, 2031, there will be a 50th anniversary ceremony at the Hyatt Memorial. Survivors, now in their 70s and 80s, will gather. Fewer each year, but the memory remains. Engineering students will attend, professors will speak, names will be read, and somewhere, in an engineering office, a young engineer will review a shop drawing, see a proposed change, and remember the lesson. Check the calculation, verify the load path. Don't assume. Because one line on a drawing carries lives. The sound that echoed through the Hyatt Regency atrium at 7:05 p.m. on July 17th, 1981. The crack of failing steel, the rush of falling concrete, the impact that shook the building, hasn't been heard again. Not because buildings can't fail. They can. They do. But because the profession learned. The music stopped once. The lobby fell silent. 114 people died in 3 seconds, and engineers worldwide vowed never again. Every calculation checked, every change reviewed, every signature meaningful. The Hyatt Regency walkways collapsed because a single line on a drawing was changed without proper analysis. They stayed fallen because the lesson was too important to forget. The memorial stands outside. The names remain. The atrium is empty of suspended bridges. And in engineering classrooms across the world, students learn the same lesson Daniel Duncan learned too late. Recognize the significance of the change, or people die.